Welcome. Today we're going to talk about a new Rust crate library called device-envoy. The goal is to make embedded programming fun. It uses Rust, Embassy, and something called device abstractions that we'll talk about more as we go. I'm an open source developer working in Rust. I have a background in machine learning, some scientific programming projects in genomics, and my other favorite programming language is Python, but Rust is number one. You can also read articles that I've written about scientific programming, Rust, and related topics for free on Medium at Carlin 8. device-envoy is an experimental library for writing microcontroller applications. The important layer that it's built on is Embassy, and what that gives us is all of Rust's async facilities. This means we can write on a $4 to $7 chip and write interesting programs without needing an operating system, as we call it, just bare metal. For now, the library works on the Raspberry Pi Pico 2, and without Wi-Fi. But there's no reason that the things described here couldn't work on other chips. And I've actually done a little bit of work. Yeah. I want this to be a talk that shows the library to you. So the way I'm going to present it is by giving demos, but I'm a chicken, so they're going to be video demos. Ready to do them live. There is a possibility of a live demo after the main talk. Then we'll see the code. How would you make the little chip do what it was that we just talked about? How do we get the little chip to do what we just talked about? And then there'll be another demo code and so on. At each step, we'll introduce one device abstraction. An example of that is the device abstraction we're controlling our D strip like this one. And the goal at the end of this is I'm hoping you'll have confidence and maybe interest in using device-envoy for your Raspberry Pi Pico projects. So let me give you the first video demo. We're on our desktop machine. We type cargo, and I've got an alias set up so that this will download a program through the USB to the chip, put a lights flash, and then all of a sudden, something happens on the LED strip. It's a little hard to see, but through the miracle of a technology called black LED acrylic, we can put it in front of our strip, and now we can see that we've turned on the lights in a blue, white pattern. So how would you code that up? With device-envoy, there's some stuff at the top, some imports, but the main thing is you use a macro called LED strip. And you tell it that you want to create a new struct type called LED strip 8, and that it's going to be controlling pin 0 on the Raspberry Pi Pico, and that the length of your LED strip is 8. Now, in your main program, you immediately call your inner main program. That's a trick I learned from Brad, and that lets us return error results in our inner main. Nothing to do with device-envoy, but I still think it's a good way to code these things. So in inner main, we initialize the hardware, and then we use our struct type to create a struct instance called LED strip 8, and we just pass it the resources for the Pico. We pass it the pin, and there's some other resources, something called PIO 0 and DMA channel 0, and that gives us a little struct. Now that we have a little struct, we're not going to use it quite right away. Instead, we're going to create a frame, a 1D frame, which is really just an array of 8 RGB pixels. We'll also create an array of 2 colors, and we'll do a loop where we go from 0 to the size of our frame, and for each position in the frame, we'll set that to either blue or light gray, alternating. That's what the mod 2 does. Okay, so now we've got this array set blue, gray, blue, gray, blue, gray. To actually write it to the LED strip, we use the write frame method we pass it this frame, and it'll appear. The LED strip will do what we want. It'll stay showing those lights indefinitely. We can go and do other things at this point. And in fact, we want this program to run forever. There's a bunch of ways to do that on microcontrollers. My favorite is to use the future pending. Wait, that just says we're never going to return any fodder. So what was the device abstraction in this case? It's a software encapsulation that from the user's point of view is just a struct, normal kind of methods and async methods. Nothing special as the user sees it. Behind the scenes, the struct is sending messages via channels and signals from Embassy. There's also an Embassy task running that will that's running in a loop, and it's processing these messages that it's getting from the struct. The task also can own resources, which is the hardware in this case, and can hold all kinds of state. Well, we need to anchor this somewhere with different ways, but they all come down to just saving it, assigning it to a static variable. And that means that it'll exist for the full lifetime of the program. And if you'd like to see something more about how this works, about a year ago, Brad and I wrote an article, How Rust and Embassy Shine on Embedded Devices. Talks about this the idea of device abstraction. Okay, let's be a little more ambitious. Instead of just setting the lights, let's have the lights blink. So how would we write a program to do this? Very similar to the previous program. Everything's set up the same, except now instead of one frame, we're going to have 2 frames. And we're going to set the first frame exactly the way we did before, but we'll set the second frame offset 1. So when one was gray, the second one will be blue, and vice versa. But there's also a new method here. There's a method called animate. So we can call the animate method with pairs. Each pair is a frame and a duration. Another frame and a duration, however many you like. And what it'll do when you call animate, it'll show the first frame. It'll wait for that amount of time. So the second one wait for that amount of time. And then it'll move back and show the first one again. So it'll just keep alternating between those two. And again, this plays in the background. So if you want to then like be watching a button or something, that's fine. This your LED strip is going to take care of itself. Okay, this is a panel, an LED panel. It doesn't look like an LED strip, but it's still an LED strip. This is still light 0, light 1, light 2, light 3. It zigzags back and forth. You can plug 2 of them, or 3 or 4 together. What's shown on the screen is 2 of them plugged together behind the black LED acrylic plastic. This program, we want to have a little gray dot, zigzag, zigzag, zigzag through the whole screen. Like so. Okay, so let's see how we would code that. We're still going to use the LED strip macro, and we're going to create a struct called LED strip 96. I'm changing which pin it's plugged into just to show that it doesn't have to be in one. I tell it the length like I did before, but now the length is 96. These are optional inputs to the macro. Optionally, we can give it a different PIO resource. It defaults to PIO 0. We can specify a non-default DMA channel, here 5. 96 LEDs is a lot. If each one runs at full brightness, that's about 6 amps. And if we're pulling our power through the Pico chip, it might not be good for our microprocessor. There are other ways you can set up the power supply, but that's the most convenient way. So by default, the library is going to limit us to 300 milliamps. But here I feel safe by bumping it up to 500 milliamps. So I've given it an optional parameter saying allowed to use up to 500 milliamps. Also, the colors on an LED aren't the same as the colors you'll see on a TV screen or a video monitor. And if you want the colors to be accurate, you have to do a color correction step, which is a parameter called gamma. There's a default one that it's usually running, but there's also an alternate one that's compatible with the library, the smart LED library. Finally, for this animation where it's going through all 96 pixels, 96 pixels is kind of a lot. And if I have 96 frames of animation, that would be a lot of memory if I want to run it in background. So I'm not going to run it in background. I'm going to do that I'm not going to use the animation command. I'm just going to do things one step at a time in the foreground. So I'll set my animation frames to 0. A nice thing about both the gamma correction and power limiting is they all compile down at compile time to just a simple lookup table that dims the LED lights and appropriately and is very efficient at runtime. So there's some more code here. We need to instantiate our LED strip 96 instance. We pass in pin 4, PIO 0, DMA channel 5. What happens if we messed up and we were still passing in, say, pin 1? It's fine. The compiler will catch the error for us. What we said when we declared LED strip 96, which was that it needs to work with pin 4. If we then try to pass it any other pin, we'll get a compiler error. So that's nice. To actually do the animation, I'm going to create another 1D frame, but now I'm going to initialize it to blue. I'm going to loop through for every index position one at a time. I'm going to turn that one index position from blue to gray, except nothing's changed yet. Then I'm going to write that big string of 96 RGB values out. So one will be gray. Everything else started out as blue. I'll have a little timer. In the array of colors, I'll set the one that I set to gray back to blue, and then I'll go through the loop and I'll set the next one to gray, and so on. And that's how we get this foreground animation. So I think that's fine, but what gets annoying is imagine trying to write a word of text onto a thing like this. You have to address in a zigzag fashion, or draw a circle, or a line. It literally a nightmare. So here's a demo where we're going to do that, and we're going to see how it works. Downloading our program, and we're just writing the word go to the display in white and in colors. So let's look at how we do text to a 2D LED display with the device-envoy library. The first thing we have to do is tell the program how this crazy display is wired. So this is actually a standard wiring, serpentine column major. So we can just say that we have an LED layout of that type and that it's 12 by 4. And that is sufficient to give us a constant that describes this. But what I actually displayed was 2 of these connected together, so we can use a combined vertical and combine 2 of those layouts together, and we get a new layout that's 12 by 8. That's nice, except we wanted to display things sideways, so we just tell it to rotate counterclockwise. And the nice thing about all this LED layout stuff is it's all done at compile time. There's no runtime cost in describing the LED. Also, if you don't want to use my cute little mini language here for describing LEDs, you can also just list the X and, like for every pixel in your LED, you can just list their X and Y coordinates if you want. That's a perfectly supported way to describe how your LED is wired. Now that we have that, we're going to use a new macro called LED2D to define a struct called LED 12 by 8 that also connects to pin 4. It uses the layout we just said, and we can specify a font that it uses. And the library has a bunch of fonts that it got from the imported most of from the Smart LED library, except we also have a version of all the fonts called Trim, where we have the letters packed together, no space in between them, which is useful for these very small displays. And then later on in our inner main, we've already created our LED 12x8 instance, and we just say write text, and we just give it the string of text. Go, new line, go, and we give it a list of colors, gray, orange, pink. And when we do that, what we saw gets displayed. As far as the colors, if you get it too many colors, there's one color per character, but if you give it too many, they're ignored. If you give it too few, it'll wrap around and recycle them. And if you don't give it any, it'll default to white text. Okay, so that's go. But what if we wanted to draw lines? Now what are we going to do? And what if we wanted to fill in the center of the circle? So that would look like this. So how do we write text, set particular pixels, and draw lines? See how that goes. We're going to create a 2D frame. It's going to know what size to be just through Rust inference, because at a much at a step way far down, where this frame is going to be written to our structure that's 12x8, and because of that, it knows that it needs to be 12x8. We're going to write text to that two-dimensional frame, go, in these colors. We can use X and Y coordinates. It's just set particular pixels to particular colors in the 12x8 array. And thanks to a wonderful crate that we're integrated with called embedded graphics, you can do all kinds of geometric things, lines and circles, other kinds of text besides the default text font that you set up. You want to draw lines, which is what we're going to use it for here. The first step is you give it a line style. This is, again, all part of embedded graphics. You say you want it to be red. Its way of describing colors is a little different than the smart LED way that we were using. So there's a conversion, but it's compile time, so there's no penalty. And we want our red line to be 1 thick. Both our frame and our LED struct know their size and their dimensions. So if we want to find the coordinates for drawing our line, we can ask how high is it and divide that 2, and that'll give us the midpoint of the Y coordinate. We can ask for where the bottom left is, what point that is. We can extract the X or Y coordinate from that. And with that, we can get coordinates for the middle left, the middle right, and we'll already have the 2 bottom coordinates. And that's all we need to draw a line from here to there and there to there. All that goes into the 2D array, which is now all created, and we just call write frame, and it gets displayed. So that's 2 of the device abstractions, LED strips and panels. Just saw they were both built on Embassy. They're built on other libraries like the Smart LED and the Embedded Graphics library. They have features I didn't show, like on 2D, you can animate 2D stuff too, just like you could for the 1D. And limits are really the limits of the hardware. You can control on a Pico 1 up to 8 LED strips independently, and on the Pico 2, you can control up to 12 independently. So let me tell you about some device abstractions that are in device-envoy, but that I don't have time to describe. My favorite one, that I'm not going to talk about, is an audio player. The audio player will play audio clips to little I to S boards, which you can get for a few dollars and just have 3 wires that you connect in. And the audio player device abstraction supports compression and runtime sequencing and real-time volume control. There's a flash array device abstraction that gives you type-safe persistent storage into microcontrollers flash memory. There's a servo device abstraction that lets you position a motor, and just for fun, it supports animation too. So you come out with a whole sequence of angles and times, and it'll do the dance and move them all. There's an infrared receiver that's supported. It actually looks like that. It knows how to decode the most common protocol. But when you do that, all you get is some kind of ugly hex numbers. There's another version of it where you can give it a table and say, if you see, when you set it up, And then whenever you push the button, you'll actually get a nice enum variant that says, oh, that was a number and it was 3, or that was the stop a push. A year ago when we were doing projects in this group with the LEDs, or with the Pico, we were using 4-digit 7-segment LEDs. There's a device abstraction for that. Another common thing people use is a display to support that. You might not think buttons need a device abstraction, but maybe we want to know whether the button's been pushed for a long or a short time. We wanted to do some debouncing, which is getting into some of the mechanical noise. All that, not that hard to do, but it's still very convenient to just not have to do it at all by having it inside a device abstraction. And another one is the clock sync. So clock sync doesn't have any hardware associated with it. It just keeps the local time, and every so often it uses Wi-Fi, it calls the time server, and makes sure that it's synchronized. Cool. Okay, Wi-Fi. How do we get Wi-Fi? So for $1 more, when you buy these chips, they have Wi-Fi, but it's a little bit annoying to program. And there's a million things you can do with Wi-Fi, but what you mostly want to do is get it to connect to your local Wi-Fi connection network, and then have this network stack that you can do things with. So, and one way, it's kind of annoying. Like, how do you get the name of your local Wi-Fi network and password in? Well, you can compile it into your firmware and download it. That's not very flexible, and it also might be a security problem. Here's a better way. You power up the chip, and it says, use your phone to connect to me. And over your phone, just tell me what your Wi-Fi ID and your password are, and I'll save it. And then I'll reboot, and then I connect. And here's what that looks like. Here it's displaying join. I connect with my phone. I look down. Oh, look, there's a Pico demo Wi-Fi provider. So this is like running Wi-Fi. On my Android phone, it says sign in. So I click that. It brings up a web page being served from this little device. I type in my Wi-Fi network. I type in a password. How we doing? Hey, it's not my real one. Yeah. And then this thing resets itself and then tries to connect to that local Wi-Fi. And after it connects, it will do a DNS call on Google and print the last 4 digits of the DNS address. And then every 15 seconds, it'll do that again. So what happens if we have this set up and we unplug it and plug it back in? You have to give the password and stuff again. No, it saved it to flash. It'll just try to reconnect. But maybe you moved it to somewhere else and you don't want to connect to your old Wi-Fi. In that case, you hold the button down. That's what the button's for. You hold the button down, and now if you do that, it will go right up to the back to join. Thank you. Also, if it tries to connect 3 times, it fails. If it tries to connect 3 times and fails, it'll also go back to join. So how hard is this to program? Not that hard. First, you set up the flash memory thing, which I said exists. I won't describe it here, but it's just setting up the typed flash memory for the Wi-Fi credentials. Then you create a Wi-Fi auto new. You give it these pins that are fixed in the Pico 2W for running Wi-Fi. You could give it a PIO resource, a DMA resource, those flash credentials. You tell it where your reset button is and which way you've wired it. You tell it the name of the local SSID. And if you want, not used here, but you can give it more things to display on that Wi-Fi sign-up page. And you can ask for things like the clock asks, what time zone are you in? It has a giant HTML pull down of all the time zones. And you can do whatever you want to get additional information there. Wi-Fi Auto, the instance, only has one method called connect. So it's going to try to connect. It will launch the setup app if it needs to, if it doesn't already have credentials. As it gets credentials and has to switch modes, it'll reset as needed. When it's all done with connect, it will be consumed and it will return a network stack and give you your button back to use as you wish. And Wi-Fi auto won't exist anymore. While it's trying to connect, it'll spit out events, and you can give it an event handler if you want. So you can say, well, when the captive portal is ready, write to whatever your display happens to be, join. When it's trying to connect, run this little animation program to show that it's connecting. If it's failed, write's failed. And when it's finally connected, maybe actions. Let me just show you what the DNS code looks like. This is mostly just nice embassy. It's not much of my own code in here. But we create a fixed memory string. We call, with our stack, we call DNS query. If we get the right kind of result back that does exist, that didn't have an error, then we pull out part of the IP4 address format string. If any of those things didn't happen, we create our -- string. And then there's a method called write text to a panel with the colors. I think we saw that before. And then it waits 15 seconds. Host DNS server account. Okay, that ended the parts where we're going to see the color. I want to show you two more demos and then do a little finishing up. So here's a demo of 3 different clocks with different kinds of displays. So they already have the local password. So they're all trying to connect, and they all have their own way to tell us that they're trying to connect. And as they connect, they get the time. They know what time zone they're in. They get the time from a time server and then display the time. Now it's showing the time in hours and minutes. And you can see each of the displays shows it appropriately. This is programmed so if you push the button, it switches to minutes and seconds. Oh, in the clock here, these servos only go 180 degrees. And it's like I don't have gears. I don't have a 3D printer. So we could call it like an elevator indicator. This is the way it's telling us. Yeah, I'm using resistors to make the arrows a little bit longer. If I find someone who really is good at hardware and wants someone who's good at software, then it would be good if we worked together, because I really only care about the software part. Here's one more demo. This is a demo that hopefully I'll be able to show live after the talk. This is Conway's Game of Life, which is a cellular autonoma simulator. Each cell lives or dies just depending on a simple rule about how many neighbors it has. So in the 16 by 16 LED panel. So this is called a glider. This pattern is well known to kind of move across, but we also worked with the IR remote, and we can make it go faster by hitting the plus button. Hit the plus button again, it goes faster still. We're going to hit, there's a pause button, so it freezes. There's a step 1 button. If you hit the mode button, it'll change color. Oh, sorry, going back to regular speed. Hit the mode button, it'll change color. And then each of the numbers is set to a pattern that it's kind of known to be interesting with Conway's Game of Life. So that's the glider, that's the default one. But if we skip over to 2, we'll get this one. I don't learn any of the other names. A couple of them are weird because I define the screen so that something's a neighbor using Pac-Man rules. If the edges, it wraps around the edges, it counts as a neighbor. It's not the normal way to do it, but it does come up with some interesting patterns because of that. The last one just puts random dots, lets them evolve until the number of dots hasn't changed for 15 generations, and then it just sets another LED, another random pattern. So that makes it kind of fun. Maybe I'll put that up on my wall. Yeah. Okay, so this is what device-envoy gives you. Let's take one example, which is the LED 4-digit 7 segment clock. When we're running that, we've got the LED needs to do something called multiplexing, which we won't talk about, but if you played with this last year, it was kind of annoying. We might want it to blink, like if we're changing time zones or something. every second or every minute, we're going to want to update the time. Separate from that, we want to be watching a button and we want to see whether we're holding the button down a short time or a long time. Separate from that, we've got this clock ticking so it can tell us when there's a new time segment. Separate from that, we've got this network connection that every so often we want to go out and connect the network. If you were to write a clock at the lowest level out Rust with timers and interrupts and shared state, it would be very annoying and it would be dangerous because maybe you accidentally assign the same PIO resource, whatever that is, to two different things that need it. And now they don't realize because nothing stopped them, assigning it twice. Just by using Rust, we get safety on our hardware, and we get type safety in our general program. So Rust gives us safety, but this is still going to be a very annoying program to write and be very fragile. Any little change would be very hard to change. Embassy was just one big step up. It gives us all the async building blocks of Rust. The ones we're using the most are tasks and channels and signals. And it means we can really do interesting things like this without having an operating system. These things that we're writing off to the chip are quite small. Device-envoy tries to go add another layer. It's encapsulating the embassy mechanisms into device abstractions. Our goal isn't to cover 100% of everything you might want to do with Wi-Fi, but if we can cover 75% of what you might want to do, which I think this Wi-Fi auto does, and make it super easy, then we've done a lot. And if we're missing anything, just create another device abstraction that covers another chunk, and eventually we'll get most of the interesting stuff done. That lets us explore what I think of as application level programming on bare metal. And by that, I mean, it actually, I hope, moves us toward making embedded programming have the simplicity of GUI or web development. Now we can program at that kind of high level that we think is appropriate for these kinds of programs. Last slide is a call to action. The first thing I'd love is anybody using programming Pico who's interested in Rust or wants the safety of Rust, use device-envoy and build some cool Pico projects. The whole project's on GitHub. I think I've spent more time writing the documentation than the code, so I believe it's reasonable to use. If I don't have every device abstraction here, so if that's of interest to you, help me expand the library, creating new device abstractions. And this is only running on the Pico. If you're really interested in something else, take these ideas and get them running on other microcontrollers. And the article is a good place to start, plus the code in the project. Right now, there's a forum for this idea of application level embassy development. And it's not just for using this library, and it's not just for the Pico. It's for anybody who's interested in application level programming on embassy. Right now, its home is just the GitHub discussion. But if anyone's interested in it, let's start there. And if enough people are interested, we'll find a bigger, better home later. And finally, if you want to see other things I've written about Rust and scientific programming, check out the Medium. Okay.
Very cool. Thank you for sharing that. Q&A?
Sure.
Obviously, that's fairly interesting to me. So I haven't got to play too much yet with Rust on embedded, but embassy is still very device specific. Is that part of what this is starting to address? Is that why this is only on embassy?
Embassy does need to be ported to each microprocessor one at a time. The Pico 1 and 2 are two of the ones that have pretty good support, but they're not the only ones that have good support. I think some of the other families might even have better support. So it's not that everything runs embassy, but more and more things do.
Okay. So if something runs embassy, can you use it with Envoy or?
Envoy is written, the problem is the things I was talking about, DMA resources and PIO, whatever those are, they're specific to the Pico. So if you want to run most of these things, they actually are, these chips are basically their own operating system. And Embassy has to be customized to them, and device-envoy has to be customized to the flavor of Embassy that is written on them.
So you could perhaps in the future get to a point where you had your device-envoy on multiple chips, and then device-envoy being a device abstraction, you could just write in that code and then twiddle some configuration.
You would hope so. If it's for a lot of these, for example, when some of the things we were saying when we just in creating a new LED strip, we had to give a PIO resource. Well, that's not going to be an input for a chip that doesn't have programmable I/O. So maybe, I mean, the worst case is we'll take as much of the design as makes sense as we create it to a new thing. The best case is maybe we'll get portable code. I don't know where we'll fall in between those two.
That's very interesting. My other thought is bare metal is it's kind of unfair to call that bare metal when you have a scheduler and has and things. I think they need something between operating system and bare metal. Say what?
Yeah, I don't.
Right now.
Here's the thing. It doesn't use it. Nowhere is it allocating memory, for instance. So that's pretty bare metal.
Yeah, I think it's important to remember that even in the Embassy ecosystem, all the abstractions you're seeing here, they do compile down to sort of what we used to write in C or, a very low level assembly language instruction, which is why we want to write at a high level, but give all the benefits of writing low level. And a C programmer would look and say, that's not bare metal. But the reality is what it compiles down to, it's actually exactly what things you writing by hand, which is pretty awesome. We're kind of spoiled that way. So yeah, it's cool.
At the risk of going off topic, I noticed from your LinkedIn that you have a Kevin Bacon number. Can you talk about that?
My Kevin Bacon number is 3 because my son is a filmmaker, but my AirDish number is also 3. So the most impressive thing is my Bacon AirDish number is 6. AirDish is how many scientific publications you have co-authored with until you get someone who's co-authored something with the mathematician AirDish.
He's kind of the most prolific mathematician because he was high on speed all the time. These are really great talk. I feel like I missed like a key thing. Is there cross compilation happening here? How's is there just like a thing running there that's getting signals from the rest that's running on the desktop?
No. This is there is cross compilation. Cross compilation. My REST desktop, which is a Windows subsystem, Linux subsystem for Windows, is compiling to the flavor of ARM that it knows is on this chip. And then I just run a shell script, which I've aliased to cargo, that just copies the firmware that it created to here. And then after that, all what this has to do is get power. Nothing is running on the desktop after the compilation has finished.
Because to check my understanding, so Embassy is not an operating system, but sort of a communication framework that then runs on hardware, and then we're sort of running about having code that interfaces with Embassy to have little sort of tasks that is checked.
Correct. Think of it as a really simple thing. If you want to set a timer at the lowest level on one of these, you've got to set an interrupt, whatever that is, with a callback, whatever that is, and all this. With Embassy, it does that for you. So you just say timer dot, I forgot the command, sleep or something, through 400 milliseconds, and it does the interrupt and whatever, but you don't have to see that. And likewise for tasks, it's cooperative multitasking. So if you really want to, you can mess up your own program, but it's still giving you multitasking on a single processor with nice responsiveness.
Just the estimates for the talk, but I was curious, could you throw up the source for one of these things that and shows how it interfaces with Embassy rather than just showing usage of them? Or is that too big for a Q&A?
I think it's too much here, but the source code's, all there.
this. It's too tight, so that I don't know if it was hands for kind of avalanche. Oh, to tell me over there. Great talk, Paul. Yeah, good to see you again. And last week, I think we were talking about dinner. Last month, we were talking about dinner. About teaching Rust through the use of microcontrollers, and I think this is a very relevant talk from that regard. I'm just trying to figure out, like, if you were to like pick on, Arduino as a application framework, right? Like it uses C and it has all this UART and debugging that kids could use in school, and the teachers could easily point out and say, hey, if you want to debug, trace debug to this UART thing, do you feel like Embassy and like your like Conway have some level of like trace debugging for someone who's trying to figure out why something's not lighting up if it's a hardware problem?
Yes and no. If someone is programming microcontrollers with Python right now, they've basically got a runtime operating system running on the chip, which makes it very convenient, but also runs 10 or 100 or 1,000 times slower than what we're getting here. With a debugger, which is a $12 gadget and plugged into, and this one, a port right there, you can set breakpoints, which I don't do very often, but you can also get trace messages. You can say info ! And get trace messages going back to the console. I use VS Code. So I find the debugging very natural, and it, I said my goal is to make it as easy as GUI or web programming. We're not making it any easier than that level of application programming.
And I have this bells and maintenance, which will alter you the same functionality to debug things.
Yeah, actually, AI loves this stuff. Just like people having the right level of abstraction makes it much easier for the AI to create. The AI already knows the idea of things like Conway's Game of Life, but it has to know how to display things to this hardware. And when the abstraction's at this level, it can do it pretty straightforwardly and efficiently.
Just sort of related to that, do you run into any challenges with like using each cycle, like because it has limited set of cycles in a given?
The only time, for a while, I was running an RFID reader. Oh, I forgot to list that. I have an RFID reader device abstraction too, and the IR, and some LEDs, and like everything I could cram on, every little thing I owned. It was running a bit slow. What I did is I moved the code for decoding the IR into the programmable I/O that the Pico offers. There was already some sample code written. It's in PIO assembly, but with C calling it, and I got it poured over to run in Rust. And now the decoder runs perfectly fast, and it needs to do microsecond timing. So it's going great.
I see Daniel and have hand up.
Oh, there we go.
Yeah, you guys hear me? We sure can. Okay. Yeah.
First of all, great presentation. This looks really interesting, especially because I just got a Pico in the mail a couple of weeks ago. But yeah, this looks like a really great educational resource. I'm wondering if you'd be interested in contacting the Teach-RS group and seeing if they would be interested in helping put together some additional embedded programming course content to go along with this library.
Sure, that would be great. And I think the video that we're making from this will kind of be the coming out party for this library. So I'm hoping everybody who's interested will kind of let me know.
Yeah, just I'll post the link to the it's the Tech Foundation, Teach.RS. It's just on GitHub. I just want to take a look there.
Okay.
I'm not sure if you uploaded anybody there already, but it's in the meetup channel on Discord. So.
Okay.
Yep, excellent work.
Thank you. I'll follow up.
Great. And just to wrap this up for time, it looks like I'll read Paolo's comment here. It says there's many Rust embedded books online that cater to specific boards, microbit, ESP32, etc. Here's the one that covers the Pod Pico. It has examples for using Embassy as well. at lower level. So there's a link in the Teams chat that may have some of the source code you're asking. That is some examples from the source code. The Embassy library also has fantastic examples, a lot of them for a lot of the different boards it supports. So look at the examples subfolder in the Embassy crate or in the Embassy repo, and you'll see many, many examples for how it's done. All right. Well, one more round of applause, please.
Thank you.